Hello, I'm Dave Brains from IBM Research UK, and I'm presenting this work on behalf of myself and my co-authors from Cardiff University, UCLA, ARL, and DSTL. The paper is titled Towards Human Agent Knowledge Fusion, HACF, in support of distributed coalition teams, and is from the DIAS-ITA research programme. That stands for Distributed Analytics and Information Science International Technology Alliance, and it's a government-funded collaboration between US and UK across academia, industry and government. It's tasked with performing basic scientific research to support military operations for a rapidly formed coalitions in a congested and contested environment at the edge of the network. The programme aims to create scientific insights and results that are relevant to future operations in the next 10 to 20-year period, rather than incremental improvements on existing technical capabilities. So this paper that I'm talking about today represents a status update on the ongoing research into this human agent knowledge fusion. So HACF is an environment in which human and machine agents are able to efficiently share complex information in a usable common format that is relevant to any given mission or operation. Key aspects of HACF are tellability, by which new information is provided generally from humans to machine agents, and explainability, which provides feedback and further detail in the form of explanations, often from machine agents. The hypothesis is that a HACF environment that supports tellability and explainability can improve overall decision-making performance through an increase in human confidence and machine performance. In this particular paper, we showcase the application of HACF through the experimental CogniSketch environment to support rapid integration of coalition sensors and analytic services. This is done in conjunction with other threads of DIAS-ITA research through my co-authors, namely selective audio-visual relevance and complex event processing. The overall goal is to show how general machine agents designed with broad capabilities can be rapidly customized by system designers to support coalition needs in a high-tempo environment, but in a human-friendly information exchange format. The humans may be unfamiliar with the machine agents, and these agents will be designed to offer broad and customizable capabilities rather than specific and fragile solutions. So HACF must enable transparency to foster trust and communication of domain-relevant local knowledge in order to customize those machine agents and support the less technical human users. Here we show the context in which analytic services can be used by a decision-maker user. The focus of this paper is on the system designer user, who must be able to rapidly provide such an environment in response to emerging situations, and can do so through the combination of existing sensors and services such as machine agents, all in a coalition context. The ability to deliver this in a realistic timeframe will depend on a number of key capabilities, and we support these in our experimental platform. For example, the ability to express semantics through ontologies, but easily extensible through a simple palette to better engage with less technical users. Also, a flexible information capture environment for use by both human and machine agents, with any kind of agent able to consume or contribute knowledge in a common form. And we have taken inspiration from the AI Blackboard architecture for this. To support experiments and exploration in this area, we have created the CogniSketch environment, which provides these capabilities as an experimental embodiment of the human agent knowledge fusion concept. In this paper, we show how this can be used to apply analytic services to sensors and to define complex events. The diagram on the right shows a typical decision-maker user being supported by augmented feeds from sensors with the potential to access explanations in real time. Our work in this paper explores the potential for rapidly building systems such as these in near real time as situations develop, and how you can bring human and machine agents together efficiently to do so. The paper contains two examples which are shown through the sketch environment, and these are highlighted on this slide. In the live demonstration shortly, I've used different sensor capability, a live webcam using standard object detection capabilities, and fed the observed entities from this into the complex event processing system. This has been a useful exercise to reapply the system to a different setting and embed new standard analytics into the environment in a short time frame, and you'll see this in the demo shortly. However, back to the two examples used in the paper. First, we show how the system designer can deploy a general activity detection algorithm and use the selective audio-visual relevance (SAVR) technology to see explanations of the results, as well as classifying those activities that are not relevant to the scene through simple actions. For complex event processing, shown on the right, we provide in the same interface an extensible palette of simple events and a simple ontology for complex event semantics, enabling the system designer to define and deploy complex event detection logic as situations arise. These complex events integrate multimodal information from sensors in a given spatio-temporal setting, along with a definition of the different simple events that must be detected and how they relate. All of this and more is extensible through the CogniSketch environment, and which could be supported by a broadly configurable generic complex event detector capability in the future. Both the saver and complex event components can be deployed as new services within the environment for use by decision makers. Okay, so let's move on to the live demo, which will hopefully make all of this a little clearer. So I'm going to give a short demo now of the human agent knowledge fusion environment, the CogniSketch environment, and I've switched from the examples given in the paper for two reasons. One is some of the feedback we got was that it looks like good work, but can we differentiate it from the other paper, which talks about these topics? Absolutely we can. That work is being presented tomorrow and is all about SAVOR, selective audio visual relevance, and some of the aspects of that and how we've got some explainability going on over video analytics. But you're going to hear all about that tomorrow. And the point of this work isn't that at all. What it's saying is we're already doing a couple of bits of research. We want to be able to bring these together very quickly and allow humans and machines to work together in this environment where they can very quickly configure and take advantage of those kinds of things, as you'll know from the slides I presented earlier. So what I chose to do last week was I thought, hey, let's actually take something a bit more interesting and a bit more live than pre-canned videos, but albeit without explanations, because the particular libraries that I chose to use just don't have rich explanation capabilities. Okay, so hello, there's a webcam. This is my simulated video camera feed, and within the frame there are things going on, like I'm here and we can do something with that, like we can get a simple object detection operation. So if I drag my function on here, and obviously you could have many of these, we've got the saver one from the paper and the complex event processing one, which I'll talk about later. But you can see on my canvas what's happening now is the algorithm is detecting a person, something of type person, and you're seeing that on the screen. Now I can turn on explanations, and as I say, this particular capability doesn't have rich explanations, but it will at least, for example, draw a bounding box with a confidence, and I've just taken the first image that came through. If I'm not happy with that one, I can remove it and it'll give me another one. If I move slightly, you'll see that, you know, how we choose to implement this is very much up to us, but I wanted a simple to understand, quick toy example. Now I've got a few things lying around, so I've got a bottle, and you can see, yes, it's got bottle. I've got a cup. There we go. Oh, it thinks it's a chair. Right, there you go, it's a cup. And I've got a banana. Okay, just random things to test this completely off-the-shelf algorithm that's running and doing object detection within the webcam, and it's obviously a completely predefined model. I haven't trained it, I'm just very much bound by what it does. But for the purposes of the demonstration I want to give you, it's ideal. It's able to identify things, and it's able to do so quickly, and this really is just a way of getting machine contributions, information coming from a machine process, onto my canvas so that I can link them into other things. I can, for example, you'll see person is here ticking away merrily. It's seeing lots of those based on the frame rate, but if I'm not interested in person, I can mark this as a regular class as per the paper, and that then effectively becomes irrelevant. If I turn back on the explanation, you'll see there's no bounding box, but if I hold up a banana, then we get a bounding box for that. So it's a really simple way of marking the classes that I'm not interested in, that I don't want to have matches for in my domain. And when you're using common models, because they're quick and they're easy, this is one of the things you might want to do, which is to suppress common false positives. And also you might want to map these classes onto something else. So I might have something that looks very much like a banana, but actually it's more, it's a completely different physical thing. But I haven't got any pre-trained models that look for that, so I might want to map the concept of banana to my own particular domain. Obviously, if you have the capacity and the time and the skills to train your own custom models, of course you do that. But what we're really interested in here with this human agent knowledge fusion environment is a very agile and rapid environment in which you can pull together pre-existing assets very quickly, experiment with them, and potentially come up with novel new approaches. And we also want to support the machine processes like this and the rich, messy information that humans have. So I just have some knowledge, I want to type it in, I want to do a quick screenshot, I want to scan in a drawing that I did, pen and paper. We want this environment to support all of that and to bring in the machine capabilities where possible. Okay, so let's switch to the second part of the demo where we talk about complex event processing. So for the final part of the demo, I would like to show how we build a complex event. Now this is at a higher level, so if you imagine we've already seen how the webcam is acting as a sensor, and that sensor is giving us events, observations of objects. But what I want to do is something higher level, and I've picked these two in the paper because it's work that we're currently doing, it's research colleagues are doing, and you're going to hear about it tomorrow. But actually the point of this environment is to allow you to embed any kind of behavior like this. Obviously we'd have to do a bit more work to make it support anything in a very fluid and flexible way, but we're already finding that this is quite an interesting environment for these kinds of experiments. Okay, so let's have a look. Let me collapse my palette here and go to my complex event processing palette. So what I want to do is define a complex event. So let's do this over in this corner. So I want this complex event to be breakfast. It's a toy example, and I only chose to do this last week, and I thought it'd be a really good test of the system to see how easy it is to actually do something completely new. So I've just dragged out an event set, which is basically a collection of events, and I'm going to link this to the complex event and say that this is the event set that initiates this complex event. The semantics here could be a lot richer, by the way, but I'm dealing with a sort of minimal set that will allow me to show something credible. So I'm going to put in an observation, and I'm going to say this initiating, it must observe first a video observation of class person. Okay, so you need a person for a breakfast, but that's not all you need. So I'm then going to drag out another two observations. Obviously there would be more efficient ways of doing this if you wanted to simply edit it, if you were an experienced user, but a lot of this is about providing an environment where configuring users can explore the options. Okay, so I've created two links here. This is of type any, and this is also of type any, and I need to make sure I specify what these things are. So from what I showed you earlier, you know that I have a banana here, and some people have bananas for breakfast, and just move that in slightly. The other thing I have is a cup. Okay, so in our very, very simple example, we're saying if you see a person and then you see a banana and a cup in any order, then you have the initiation of a breakfast complex event. But we need to terminate these events too, in most cases anyway. So I'm going to drag on here an event set which is the terminated set. Now, I want this to be basically when the person leaves. Now, I could drag the person down here and create a second link, but it's a little bit confusing because I want the first one to appear here, and it doesn't actually matter. I can have as many instances of these as I want. So I'm going to, create here that when there is not a person, then the complex event of breakfast is terminated. Okay, so we have almost everything we need. I now want to provide a very simple temporal constraint. So I want to say that this is within seconds. You may have others, and I will give it a value of 5. That seems reasonable for what we're trying to do here. Okay, so that's our complex event defined. We're almost ready to go. So from a function point of view, I have a complex event processing function. Okay, so this is the thing that is now listening to see whether these conditions are met. Okay, now I think you can see where we're going with this. So I am able to detect all of these things, but in order to do so, I need to drag myself out a webcam. Okay, so here we go. Here is the webcam. And actually one thing that is really useful for arranging your knowledge, if you like, is I have this header. These are simple label nodes, and I find this kind of thing quite useful when you have the more complex graphs, and I'll show you one of those in a minute. So I'm just going to chuck that one there, and I'm going to have CEP over here just to show the different parts of my screen and how they're laid out. Okay, so there we go. So this is the CEP definition. Let's move that one down there a little bit. And what I want to do is link the webcam to the complex event processing. Now I can add things like spatial constraints, but I'm not going to do that because this is all running off this single local webcam. So the final thing we need to do then is drag on our object detection like we have before. We'll just give that a moment to load. And there we go. You can see it's detecting me, it's detecting a person. If I turn on the explanations, you'll see the bounding box. Okay, so let's give it a go. So there's my banana, wonderful, and there's my cup. Now, did I do it fast enough? You'll also see that it's falsely thought that was a remote. Yes, I did. Here we go. Here's my first breakfast. So you can see complex event processing has identified breakfast at 1942. Gosh, it's quite late for breakfast. So to terminate this event, what I really need to do now is leave the frame for 4 or 5 seconds. So let's just wait, and then I will come back. And you can see the description has changed for this breakfast event. So it says it lasted for 24 seconds. And you can see here is the start, finish, and duration. And all of this is defined by the complex event that I've drawn over there. Let's give it one more go. So I'll try both at the same time this time. Come backwards slightly. There we go. Now we have a breakfast at 1943. And if I move out of the frame again, we should see that within 5 seconds. Finish. There we go. Now, remember, the point of this is not to show off how good we are at doing complex events, because that's A, someone else's research, and B, I've done a really trivial model here so that I can demonstrate it in the feasible time. But what we are demonstrating is this ability, let me just turn off explanations, to create a canvas within which you can do many, many more things, lots of information from humans, messy information, not necessarily formal. So I might drag on a picture of breakfast and link it to one of these events. I might be an analyst or something who's actually offering some opinion here. I might have some text. I might want to say over here, for example, if I drag on a text node, I might want to say something like, not everyone has fruit for breakfast, or, you know, it doesn't really matter. All I'm showing you here is that the point of this environment is to support this kind of free-form exploration where you have machines able to contribute information and you have humans able to contribute information. And the whole point of the human agent knowledge fusion environment is to allow, to provide something that's flexible enough and extensible enough for all of this to come together in a way that relatively non-technical people can take advantage of. You probably wouldn't build your production systems this way, but it's hopefully a really good environment for experimenting and exploring and helping people gain confidence in machine systems. Thank you for listening. So, thanks for watching the demo. This work is ongoing within the DIAS ITA research programme, and we will continue to investigate new techniques for information integration in the context of human agent knowledge fusion within this CogniSketch environment, including uncertainty information. We have plans for 2 experiments to explore the tellability and explainability aspects of the HackF concept, using a combination of online platforms such as Mechanical Turk from Amazon, and a collaborative human team of subject matter experts attempting to perform a complex information-intense problem-solving task with support from machine agents. These will be measured with a mixture of quantitative and qualitative measures for the first and second experiments, and to see whether measurable impact can be found in different settings. There are a number of previous publications that define the HackF concept, and related work around conversational explanations and links to various other resources are provided on this page. So, in summary, The technical contribution of this work so far is to outline the way in which generic services can be composed into situation-specific applications with minimal technical effort by system designer users. Tempo is very important as it is not credible to predefine such systems in advance to cover all possible situations that may arise. Given our coalition and edge of network operating context, it is important to create and deploy solutions rapidly, and the platform and worked examples both in the paper and today's live demo show how this can become possible. Thank you for listening to this talk.